Commonwealth Avenue, or Don Mariano Marcos Avenue, is the widest road in Metro Manila and the entire Philippines. Lying in the northeastern part of Metro Manila and Quezon City, it caters 221,759 vehicles per day to and from the business centers of the city and the southern part of the metropolis. It has a 95-meter road right-of-way, or RROW, from Quezon Memorial Circle up to Doña Carmen, a full 8-kilometer stretch representing 67% of its entire length of 12 kilometers ending at Mindanao Avenue. Before the start of the development project, the road has a variable width of 5 to 8 lanes, and most of the areas beyond the pavement are occupied by informal settlers and commercial establishments. With that situation at hand, we in MMDA knew that it will take the long-known political will and determination of the Metro Chief and the cooperation of the local government of Quezon City, the understanding of all sectors and the entire community as well, to substantially clear the obstruction and give way to the continued progress of the development plan. To start the project design, we have set the following criteria. First is to acquire the full 95-meter road right-of-way. The road must have a safe and continuous flow, intersections with minimal delay, average speed of 50 km per hour, and design speed of 80 km per hour. We also must have minimum obstruction and eliminate concrete barriers at U-turn slots. Finally, we should provide space for mass transportation system like LRTs, MRTs, tram, BRT, etc. Now, what are we going to do with the 95-meter road right-of-way? We can have a 10-lane road each direction with enough sidewalk, bike lane, and planting strip. But traffic engineering view stated that we should not. Why? First reason is that there would be a safety hazard on high-speed conflict. When you are traveling on a highway at 50 to 80 kilometers per hour, you would be taking a dangerous movement from innermost to outermost lane when exiting to the abutting street or side street establishments. The same way in entering to the innermost lane. This is the same reason why no traffic engineer around the world assign 10 lanes side by side on high-speed highway. Let us take a look at the widest roads in modern countries around the world. Exceptionally wide Interstate 75 in Atlanta, with 8 lanes each direction. Zagreb, Croatia is 70 meters wide, but only has 6 lanes, 3 lanes each direction. I-75 Georgia, 8 lanes plus shoulder. Netherlands, A16, 5 lanes between dividers. A4, the western part of the ring road around Rotterdam, about 95-meter RROW, similar to our Commonwealth Avenue, but only have 2 to 3 lanes between dividers with shoulders. Acceso Norte Highway, or Northern Access Highway in Buenos Aires with 18 lanes, is the widest highway in Argentina, 6 lanes maximum between dividers. Netherlands, A15 southern part, 6 lanes maximum between dividers. Second reason why we should not assign a 10-lane carriageway is the vehicle conflict and traffic management problem on junctions. We have at our hands is a 20-lane highway crossing against a 4-lane road. Commonwealth Avenue has 4 full intersections and at least 8 T-junctions. This kind of junction will give 228 vehicle-to-vehicle conflict, a situation that traffic engineers like very much. First, because it would give them a challenging job, and second, it would assure the need for their expertise and continuous job, of course. The foregoing considerations dictate that we have to reduce the number of lanes. Commonwealth Avenue, with closely 222,000 vehicles per day, 11,000 of which pass the road during morning or afternoon peak hour, would need at least 5 lanes each direction. Considering the future increase in vehicular volume, 7 lanes per direction will be assigned. What are the traffic engineering solutions to address the conflict? First, we can install traffic signal light facility at 5 million pesos plus 2.5 million maintenance expenses per year. Second, we can construct conventional interchange using 5 flyovers up to 4th level with footbridge or signal light for pedestrians. This would cost us about 1 billion up to 3 billion. Or we can construct elevated U-turn interchange for about 400 million. Another simpler solution is the at-grade U-turn, which would need about 30 meter space at the center for the turning radius of long vehicles. This would cost only about 2 million per set and 24 million for the footbridge. Obviously, the most economical solution, besides being one of the schemes that satisfy the design criteria and the need for the reduction of the number of lanes on the carriageway for the safe and continuous flow of vehicles, will be the provision of at-grade U-turns. Now let us look at some existing wide roads in other countries that utilizes traffic signal lights facility as the intersection traffic management. This is the 9 de Julio in Buenos Aires, Argentina during off-peak hours, 9 lanes per direction with traffic lights. And this is the same avenue during peak hours. Note that in a road stretch with multiple signalized intersection one after the other, the delay per vehicle add up in each intersection. The result? Accumulation of vehicles, especially when the volume is nearly equal to the road capacity. A picture of a similar wide roads in Moscow taken sometime in October 2007. Based from the foregoing presentation of criteria, restrictions, and considerations, we will now draw the comprehensive concept of what the development would be. On the upper portion of the screen is the general cross-section and plan in the lower portion. From the 95-meter road right-of-way, we will have bike lanes in the outermost portion, a 3-meter walkway along the curb side, and planting strip between them to provide shades and fresh air, and to serve as the dividing line that separates bikers from walking pedestrians. The road pavement shall accommodate 2 lanes for public utility vehicles and 5 lanes for private vehicles. The U-turning vehicles in the emergency area will utilize portion of the middle strip, separated from the 7-lane mainstream of through traffic. We will also provide footbridges about 500 meters distance along the stretch and overhead signs on it or on separate gantry structures. Okay, let's have a checklist. What we already have are bikeway, walkway, planting strip, public utility and private vehicle lanes, U-turn lanes and emergency areas, footbridge, overhead signage. Of course, we must have lighting, which we will install on high-mast poles. The service poles should be on the outer limit of the road right-of-way to avoid obstructing the bikers. On the side street regulation, the setback provision of PD 1096 or the National Building Code of the Philippines latest edition shall prevail. This calls for an 8-meter setback from the road right-of-way limit or the private property line going into the property. This area, which is within the private property, will assure that the owners of the establishment will have ample space for parking. In short, the law does not allow construction of any permanent structure within this area. If we intend to have a continuous flow of vehicles throughout the whole stretch of the road, the design of at-grade U-turns should stick to the following requirements. There should have enough turning radius to allow safe, smooth, and continuous U-turn maneuver without the need for concrete barrier, and in such a way that the through traffic would not be obstructed. As you can see, the design of the U-turn will accommodate light vehicles only at the inner radius and long vehicles at the outer radius. Small vehicles may also use the outer radius when no long vehicle is using it. After the final decision for the design concept, the next task of the traffic engineers is to prepare the detailed engineering design. First, we conducted physical inventory of the existing road. Gather traffic and pedestrian data, including the turning movement of vehicles within each of the existing intersections, pedestrian count at every possible location of footbridge, and the passenger data at loading and unloading areas. Traffic engineering design includes preliminary structural design using STAAD Pro, a structural analysis and design software. Next is roadway design using Path Planner and CAD, or computer-aided design and drafting. The center's traffic engineers and computer operators include technical personnel dedicated to traffic analysis and computer simulation. The overall traffic design will be confirmed by the traffic simulation showing all the design parameters and data inputted in the computer. The result is being fine-tuned until the best combination of geometric design and proper flow distribution, taking into consideration the local situation, pedestrians and drivers' behavior in the actual scenario. After foregoing activities have been perfected, the road furniture and landscape is included for the development of presentation materials as what is being shown here. The Commonwealth Avenue Development Project is one of the 7 major roads projects that have been selected by the MMDA in order to prioritize the inflow of activities at the most congested but important arterial roads in Metro Manila. The scheme of clustering the projects into 7 ensures that each stretch of road will be substantially completed at the least expense so as to create positive impact on the motorists. When completed, the designers hope to achieve the following targets. First, the RROW shall be preserved for use of the vehicles, passengers, and pedestrians and shall demonstrate that there is indeed a government determined and responsive of the need of the transportation sector. Second, it shall completely assert the roadway policy from the main carriageway up to the equally important sidewalk as stipulated in PD 1096. Third, save several billions of pesos a year in the economy due to fuel and personal time savings brought about by the elimination of congestion and reduction of carbon emission and health benefits, to name a few. And fourth, reduction of accident due safe design, appropriate geometry, and consistency of traffic movements.